Hey guys, welcome back. Today we're going to be looking at groundwater, so let's go ahead and get started. I'm going to go ahead and warn you that there's a lot to cover here, so feel free to pause the video to gather the words as we go through. So what is groundwater? So if you drill a hole deep enough anywhere on Earth, it will start to fill with water, even in the desert. Groundwater is present everywhere beneath the surface of the Earth, but it is only a small fraction of all the water on Earth. Okay, so we've already talked about the hydrosphere, and we said that 97% of it is oceans. All right, of all the freshwater, more than 70% is found in the ice caps and glaciers, and the remaining freshwater is groundwater. Only about 3% of it makes up water above land. So let's talk about precipitation. Much of the precipitation that falls on the Earth enters the ground through the process of infiltration, and it ends up becoming groundwater. Groundwater slowly moves through the ground, and eventually it returns to the surface through springs and then flows back into the ocean. So how is groundwater stored? All right, so puddles, when they appear, they either disappear through evaporation or partly through percolation into the ground. On sandy soils, rain soaks into the ground almost immediately. Subsurface earth materials, if they're are not totally solid. They contain little openings or pores, and that makes up much of the materials that make up. The amount of pore space is called porosity, all right, and enormous amounts of groundwater are stored in just the pore spaces of rocks and sediment. So let's talk about the zone of saturation. All right, the depth below the Earth, which the groundwater completely fills all the pores, is called the zone of saturation. So when you reach somewhere in the Earth and all the pores are filled with water, we will call that the zone of saturation. The upper boundary of this zone is called the water table. Only the water in the zone of saturation is called groundwater. All right. Above the zone of saturation is the zone of aeration. This area is moist, all right, but most of the pores contain air, all right? The water in the zone of saturation is either gravitational water or capillary water. Gravitational water is water that trickles downward as a result of gravity, and capillary water is water that is drawn upward from the water table and is held in the pore spaces as a result of surface tension. And this is similar to the action of water that is drawn up through the pore spaces of a paper towel when one end is dipped into the water. So if we were to take a paper towel and dip it into the water, water would move up, and that would be capillary water. This is the same action. The depth of the water table varies depending on local conditions. When you're in stream valleys, the water table is only a few meters deep. And when you're in swampy areas, the water table is almost at the Earth's surface. When you're in hilltops or arid regions, it could be hundreds of meters down before you reach the water table. Water table rises during wet seasons and drops during dry seasons. So groundwater always flows downhill in the direction of the slope of the water table, and it is a slow movement because the water has to squeeze through numerous tiny pores. The ability for water to pass through those pores is called permeability, and materials with large pores such as sandstone, limestone, sand, and gravel have high permeability. Things that are very fine grained, such as silt, clay, and shale, are called sometimes impermeable. Clay is so impermeable that it is used to line ponds and landfills because it really prevents the movement of materials through it. So let's talk about aquifers. So the flow velocities, or the speed at which it flows through permeable materials, are always higher than the speeds through impermeable materials, regardless of the slope of the water table. So most groundwater flow goes through permeable layers that are called aquifers. All right, impermeable layers are called aquicludes and are barriers to groundwater flow. So let's look at some groundwater systems. So when things are moving, we have various different things happening. All right, so looking at groundwater systems, the average length of time that water remains underground is several hundred years. It is moving slowly but continuously through aquifers and eventually returns to the Earth's surface. In some cases, it moves against gravity. When it emerges where the water table intersects the water surface. And the exact places where groundwater emerges depends on the arrangement of aquifers and aquicludes in a particular area. So where is this water coming out? And it's coming out at springs. So as I said, aquifers are permeable underground layers in which the groundwater moves. Aquicludes are, again, those impermeable layers. Groundwater tends to discharge at the Earth's surface where an aquifer and an aquiclude come into contact. And these natural discharge areas are called springs. So springs occur in various places, such as the sides of valleys and at the edges of perched water tables. And the water that flows out of a spring, the volume of water varies from the flow of a small spring to the rush of a large river. So it can be different. You can see different flows of water. So the temperature of springs. So spring water is generally thought of as being cool and refreshing, but actually the temperature of groundwater that is discharged through spring is generally the average annual temperature of the region where it is located. And groundwater is colder in the summer and warmer in the winter. In some regions of the United States, certain spring discharges is much warmer than the average annual temperature, and these are called warm springs or hot springs depending on their temperatures. Hot springs have temperatures higher than that of the human body, and most of these are located in the western United States, though there are hot springs in North Carolina. There are a number of hot springs that occur in the eastern states, and they emerge from aquifers that descend to great depths in the Earth's crust, allowing deep hot water to rise. So among the most spectacular feature produced by Earth's underground heat are volcanic regions are called geysers, and geysers are explosive hot springs that erupt at regular intervals, such as Old Faithful and Yellowstone as shown here. All right, wells are holes that are dug or drilled deep into the ground to reach a reservoir of groundwater. And they tap into the aquifer. The simplest wells are those dug or drilled below the water table into the zone of saturation into what is called the water table aquifer. So we can see some images here that show wells. When wells are overpumped, it lowers the water level and produces what's called a cone of depression in the water table around the well. The difference between the original level and the new level because of the pumped well is called the drawdown. And if many wells withdraw water from the same water table aquifer, their cones of depression may overlap and cause an overall lowering of the water table, which can cause shallow wells to go dry. Water from precipitation and runoff is added back to the zone of saturation in the process that is called recharge. If recharge does not keep up with the pace of withdrawal, the water table continues to drop until all the wells in an area go dry. All right, let's look at confined aquifers. Water table aquifers that are unconfined and unprotected are easily polluted. Surface spills of pollutants often reach the water table and spread through the aquifers. More reliable, less easily polluted water supplies can be found in deeper aquifers called confined aquifers, which are sandwiched between aquicludes. And aquicludes form barriers that prevent pollutants from reaching those aquifers. All right, let's look at artesian wells. Because the area of recharge is usually at a higher elevation than the rest of an aquifer, a confined aquifer contains water under pressure, and this is called an artesian aquifer. And when the rate of recharge is high enough, the pressurized water in a well drilled into a confined aquifer can spurt above the land, and this causes a fountain or an artesian well. The spring that discharges the pressurized water is called an artesian spring. So let's talk about threats to our water supply. So fresh water is Earth's most precious natural resource. We've read about this so far in this unit, and you can't live without water. And humans put enormous demands on fresh water. Not only is water used in households, but is also used extensively in agriculture and industry. So groundwater supplies much of this water. Groundwater supplies can easily be depleted, and if groundwater is pumped out at a rate greater than the recharge, the groundwater supply will inevitably decrease and the water table will drop. For example, the Ogallala Aquifer, which has rapidly decreased over the years. Another problem caused by excessive withdrawal of groundwater is called subsidence and results in a sinking of the land, which we can see here with the Leaning Tower of Pisa and also this house that is going down because of subsidence. Pollution in groundwater. The most common sources of groundwater pollution are sewage, industrial waste, landfills, and agricultural chemicals. And they enter the ground above the water table but are eventually flushed downward, infiltrating precipitation and becoming mixed with our groundwater. And in those highly permeable aquifers, all pollutants, including raw sewage, can spread really quickly, and that can spread diseases. Chemicals that are dissolved or transported with groundwater in the form of either ions and molecules, so they cannot be filtered out in fine-grained sediment. So when we put fertilizers in when we get fertilizers in our water, just filtering them won't get them out. So chemicals such as arsenic can contaminate aquifers, and they can't be easily removed. All right, let's talk about salt. Not all pollutants are toxic. Ordinary table salt is used widely to season food. However, salt water, like at the beach, when the salt content is too high, it is not good for us. And that's one of the major threats to groundwater supplies, especially in coastal areas. If you ever go to the beach, the water is generally not great. So the groundwater near the Earth's surface is underlain by a denser, salty seawater. If we pump the wells too much, it can cause the salt water to rise into the wells and contaminate the freshwater aquifers. All right, let's talk about radon. So another source of natural pollution is radioactive radon gas, and it is one of the leading causes of cancer. Radon is generated by radioactive decay of uranium in rocks and sediments, so it's naturally occurring. Some rocks, especially granite and shale, contain more uranium than others. The groundwater in the areas where these rocks are present contain more radioactive radon than normal, and so then the radon can seep into houses, and you have to have a radon pump to help get it out to reduce your risk of cancer. So how can we protect our water supply? So there's multiple ways. We can make sure that major pollution sources are identified and eliminated as much as possible. Pollution plumes can be stopped by building of impermeable underground barriers. Polluted groundwater can be pumped out for chemical treatment on the surface. However, none of these measures alone can save Earth's water supply. Humans simply need to become more aware of how their activities impact the groundwater system. So let's talk about groundwater erosion and deposition. So groundwater is slightly acidic and it attacks carbonate rocks such as limestone. Limestone consists mostly of calcium carbonate, which makes up chalk. All right, so it dissolves easily in any kind of acid, as we saw in our vinegar and chalk experiment we did with weathering and erosion lab. Both dissolution and formation of calcium carbonate plays a major role in the formation of limestone caves. So caves are natural underground openings with a connection to the Earth's surface. Some caves form passages, shafts, and chambers that can stretch for kilometers. They have structures that hang from the ceilings. Some caves are dry, others contain underground streams or lakes. Others are totally flooded and can only be explored by cave divers. Most caves develop in the zone of saturation just below the water table. As the groundwater percolates, it gradually dissolves the adjacent rock and enlarges these passages to form interconnected networks of openings. Eventually, the water table lowers until much of the cave is filled with air, and new caves form beneath the lowered water table. If the water table continues to drop, the limestone formations become honeycombed with caves and caverns. So natural deposits. The most remarkable deposit produced by groundwater are the dripstone formations that decorate many caves. And these are built slowly as water drips through the cave. The water loses some of its carbon dioxide and deposits a tiny amount of calcium carbonate. And these form cone-shaped cylindrical structures called stalactites that hang from the ceiling, or the water drop falls to the floor and gradually builds a mound, and these are called stalagmites. And then the two can grow together to form a dripstone column. These formations are composed of limestone called travertine. All right, karst topography. So the dissolution of limestone produces surface features such as sinkholes, which are depressions in the ground caused by the collapse of a cave, or the dissolution of bedrock from acid rain or moist soil. Dry valleys are when the surface stream drains into a cave system and continues underground, which causes a sinking stream. Limestone's regions that have sinkholes, sinks, and sinking streams are said to have karst topography. Prominent karst regions in the U.S. are located in Kentucky, and most of the lakes in central Florida are actually sinkholes. And actually, this little band right here is where my grandparents and great-grandparents lived in Florida. All right, groundwater deposits. Your tap water contains various dissolved materials. Some contain sulfur, some contain iron. Water that contains iron can leave a brown or red stain on kitchen and bathroom fixtures. So you can see these things in your own home. Sulfur-containing items smell like raw, nasty eggs, like rotten eggs. Hard water. So we would call something hard water when it has a high concentration of calcium, magnesium, or iron. It's common in areas that have a lot of limestone, and deposits of calcium bicarbonate will eventually clog the water pipes, and this can be controlled using a water softener. And water that contains few dissolved ions is called soft water, and the Charlotte area has very soft water, which has its own challenges.